Using Lagrange multipliers, I want to solve a financial problem related to the portfolio optimization based on the so-called Markowitz model. Let me write down Markowitz. I think the spelling is correct. But anyway, this is a Markowitz model. It's a model which regards investment portfolio, in particular the return of an investment portfolio while minimizing the risk that's related to the portfolio. Now, let's introduce the problem. It's not so difficult to introduce the problem. The goal here is to optimize the portfolio for an investor to achieve the best possible return while minimizing the risk. In particular, the risk is represented by the variance of the portfolio. Therefore, the problem is to minimize the portfolio variance while maintaining a given return. So let's try to write down the equations and also let's explain the symbols. In particular, let's define mu I first. So mu sub I is the expected return of the ith asset. So we assume that we have 1, 2, 3, n assets, and the expected return of each of them is mu I. Then we have wi, which is the proportion of wealth invested in the ith asset. So, for example, we invest a certain percentage of our wealth into the ith asset, and this means that omega 1 plus omega 2 plus dot 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 plus omega n must be equal to 1. So these are like weights related to the asset. Then we have sigma ij, which you can think of as a matrix because you have two indices. This is the covariance between the two assets I and j. So there is some kind of relation between the ith asset and the jth asset, which is described by this covariance matrix object. The expected return, which is mu p, and variance sigma p squared of the portfolio, so P stands for portfolio, mu P will be given by the sum of omega I mu I, and you sum over I from 1 to n, whereas the risk, so this sigma P squared, is a sum over I and over j. Let me write it like this, but it's a sum from 1 to n. Then you have omega I sigma ij omega j. So these are two equations, and we want to minimize the risk, so we want to minimize this function, which is subjected to some constraints. In particular, we write down a certain function that I call L, which stands for Lagrangian. It's a certain function that depends on omega 1, omega 2, dot dot dot, omega n, so it depends on the weights. And then it also depends on two parameters, lambda and gamma, which are the Lagrange multipliers. Now let me show you how they appear into the definition of this function. So this function is simply equal to sigma p squared, which we can write like this. So we use the definition of it. So summation over I and over j, omega I sigma ij, omega j. Then we have minus lambda, which is the first Lagrange multiplier, and then we have the first constraint here. So the first constraint is this. So we can write it as mu p minus summation over I from 1 to n, omega I mu I. So mu p is considered to be a constant. So we want to fix the expected return, and the variables are these omega 1, omega 2, omega 3, omega n, and if you want, we can consider these two Lagrange multipliers as variables. And then we have minus the other Lagrange multiplier, which is gamma. And then we have the last constraint here, which is this one. So we can write it as summation over I from 1 to n, omega I minus 1, like this. Now that we have written the problem in this fashion, what we have to do is we have to take the partial derivatives of L with respect to the omega I, all these omega I coefficients, and set it equal to 0. And then we also have to take the derivatives with respect to lambda, set it equal to 0, and also the derivative with respect to gamma, and set it equal to 0. So these two equations will simply give us the two constraints. So this first one will give us basically this equation here, and this second equation will give us these other constraints. So basically they are just a different way of writing down the constraints. Simple as that. Whereas the first equation here will give us the following. So when we take the partial derivative of this expression with respect to omega I, well, you have to remember that I here is a dummy index because we are summing over I, and this J is also a dummy index. So for one of these I's and for one of these J's, those coefficients will be equal to this fixed I here. So maybe I could have called it K instead of I, but it's the same thing basically if you think about it. What you get when you take the partial derivative of this is a factor of 2, because first you can take the derivative of this, and then you can take the derivative of this. You can think about it, and then you can write the rest as summation over j, and it's a summation from j equal to 1 to j equal to n, and you have sigma ij omega j. Then you have minus lambda mu I here, and then you have minus gamma equal to 0. Simple as that. Now from this equation here, you can also take the inverse of this matrix. So you can see that this equation can be written in matrix form. So you have the matrix sigma, which multiplies the vector omega, then you have minus lambda, you have the vector mu, and then you have minus gamma, and then here you have to think that gamma is multiplied by the constant vector 1. So this vector 1 here should be interpreted like this. You have n ones, like this, equal to the 0 vector. Then you can take the inverse of this matrix. So you can rewrite it as omega equal to 1/2. Then you have lambda sigma inverse mu vector plus gamma sigma inverse applied to the vector 1. And if you want, you can also rewrite it in index notation. So you can write omega k equal to 1 over 2 lambda. Then this can be written as a summation over a certain index I. You have sigma inverse ki mu I plus gamma, and then you have the summation over I of sigma inverse ki, which multiplies 1. So basically you can write it like this, and this is the expression for omega k that you can see. I mean, it depends on lambda and on gamma, and they are not really known. So how do we find lambda and gamma? Well, the idea is to use the constraints, basically these two equations, so this one and this one. Now that we have found an expression for omega k, which depends linearly on lambda and on gamma, you can put basically this expression into this constraint and also this constraint here. So when you do that, you will have two equations that depend linearly on lambda and on gamma. And you can solve for them. So you will find the solution for lambda and for gamma. The two equations for lambda and for gamma will contain lambda and gamma, of course, but they will also contain these coefficients here, the mu I and sigma ij, which we assume to be given. So we can find lambda and gamma and then substitute back into this expression here, or the one with the subscripts. So you can find a formula for the generic omega k And basically, these formulas can be used to minimize the risk, as we have seen. Just for the sake of completion, let me write down the formulas for lambda and for gamma. So in particular, let me remind you that we have one formula like this. We have to sum over I omega I equal to 1. So we can substitute this with the index I replacing k, and we obtain the following. So we can write 1 equal to lambda over 2 summation over I and over k, because now I'm using the formula summation over k of omega k. So I'm writing it like this, so I can substitute it directly. Therefore, this formula, this summation will become a summation over I and over k, because we also have to sum over k. And we have a sigma inverse ki mu I plus gamma over 2 summation over I over k sigma ki inverse. And similarly, we also have another formula like this, summation over k omega k mu k equal to mu p. So you can do the same, mu p equal to lambda over 2 summation over I over k sigma ki inverse mu I mu k plus gamma over 2 summation over I over k sigma ki inverse mu k. So you can see that we have two equations that are linear with respect to lambda and to gamma. So you don't have to be confused by these somewhat complicated expressions, because these are given data. So you can consider them to be given, and you can substitute for lambda and for gamma. So you can solve for lambda and for gamma and substitute them into this expression here to find the generic solution for omega k.